Hello everyone, and welcome to an introduction to the K-nearest neighbors lecture. In this lecture, we'll discuss the K-nearest neighbors algorithm and how to use it for classification problems. If you want to understand the complete mathematics behind this algorithm, go ahead and finish reading Chapter 4 of an Introduction to Statistical Learning. K-nearest neighbors, sometimes known as KNN, is a classification algorithm that operates on a very simple principle. It's actually just best shown through example. Imagine we have some imaginary data on dogs and horses, with heights and weights of these dog and horse data points. If we plot them out, it looks something like this. Again, this is just imaginary data, so don't worry about the weights and the heights. Obviously, you're not going to have a 500-pound dog. But here we have red points indicating horses and blue points indicating dogs. This is our training data. What we want to know is if we get an animal where we only know the height and weight, we want to predict if that new data point is a horse or a dog. Again, we're just trying to classify this new data point. Here, we can kind of already see that based on where the green point lies in association with its neighboring points, it's kind of easy to predict certain points. For example, this top point in green would probably be a horse, since all the points around it are red horse points. Likewise, the point all the way at the bottom left that's green would likely be a dog, since the nearest points to it are all blue points indicating they're dogs. We want to expand on this idea and formalize it. That's where K-nearest neighbors algorithm comes to play. The training algorithm is very simple. You simply store all the data. And the prediction algorithm for new test points works like this. You calculate the distance from x to all the points in your data, x indicating that particular new data point. Then, you sort the points in your data by increasing distance from x. Then you predict the majority label of the k being a number, closest points. Choosing a k will affect what class a new point is assigned to. Let's go ahead and look at another example. Here, I've plotted out our training data, which is just yellow points in class A and purple points in class B. This red star indicates a new point. I want to predict whether this point belongs to class A or class B. If I choose k equals 3, then I look at the 3 nearest neighbors to this new point. In this case, I have 2 purple ones and 1 yellow one, or class A. So with k equal to 3, I will predict that this new red star point belongs to class B, purple. However, if I set k equal to 6, I will actually have a majority of yellow or class A points, meaning if I had k equals to 6, I would predict that this new point belongs to class A. Choosing a k will affect what class a new point is assigned to. So if we look back on our horse versus dog, we can here see the plotted effects of various k values. If I choose k equals to 1, I'm going to actually pick up a lot of noise. But as I go larger and larger k values, you'll notice I smooth out and create more of a bias in my model, where I get a cleaner cutoff at the cost of mislabeling some points. The pros of the K-nearest neighbors algorithm is that it's very simple, the training is very trivial, you just sort your data, it works with any number of classes, it's really easy to add more data, and it has very few parameters. The only parameters being the k, which is how many points are you going to look at that are next to your new test point, and then whatever distance metric you're using. If you want to learn more about distance metrics, go ahead and finish reading Chapter 4. But the distance metric is just how you're actually defining mathematically the distance between your new test point and the old training points. The cons of this algorithm is that there's a high prediction cost, and it's worse for large data sets. Because you're having to sort this entire large data set, there's a high prediction cost in testing out what points are closest to this new data point. It's also not good with high dimensional data. As your features increase and you get higher dimensions in your data, it's going to throw off your ability to measure distances in various dimensions. Also, categorical features don't work well with k-nearest neighbors. Now that we've discussed the theoretical background behind the k-nearest neighbors algorithm, let's talk about the upcoming Python projects. A common interview task for a data scientist position is to be given anonymized data and attempt to classify it without knowing the full context behind the data. A lot of times, these are known as take-home tasks, where you're given a data set, but you don't actually get the knowledge of what each column represents. We're going to simulate a similar scenario by giving you some quote-unquote classified data, where what the columns represent isn't known, but you're still going to have to try to use KNN to classify the data into different classifications. Okay, thanks everyone, and I'll see you at the next lecture.